Oh, welcome. Let me walk you through some of the tests, not all of it, just to make sure we're all on the same page. So right here, I'm showing section 3. This was the problems. So you might remember we want a circuit that outputs this, given 5.05 volts. The problem is we only have a few resistors that we can choose from. So we've got our power source, only one of each of the following resistors, and we want to create that. And then there's a second part, which is a little bit more complicated. But first thing is, anytime I'm trying to step down the voltage, I want to use a voltage divider. So we have an R1 and we have an R2. And then I'm going to take that and connect it as such. That's going to give me a positive voltage. We're not using any op amp here. Now the equation, so E out, and this is on the equation sheet, is equal to R2 over R1 plus R2 times the input voltage, which is 5.05. So I already know two of these things. So we want 0.326 volts. We don't know which resistors we're going to use, but we know that this is 5.05 volts. And so therefore, this thing needs to equal 0.0646, let's say. So at this point, there's not really an easy way. We don't have Excel available to us, but you're just going to plug in numbers. Now, I know this is small, so I can start with a pretty high number for R1 and a small number for R2. And so we should find that R2, a really good, which is crazy, it actually works out pretty well, is R2 is 47 ohms and R1 is 680. That gets us about that same ratio that we're looking for. So that is the equation for a voltage divider. Anytime I'm trying to step down the voltage, all I need is two resistors. Or, in the case of labs, we can tie them together. But this was the answer for part 1. Now, part 2 is where it gets a little spicy. Stay tuned. So I go to the next slide, and there's nothing there. But now we want to find the uncertainty of the output voltage. Okay. So let's see, what is the output voltage? Well, let me start with the equation. E out is equal to R2 over R1 plus R2 times E in. That's the equation we just used. And we have some terms here. We're trying to figure out the uncertainty of E out, which is on the left-hand side. So let's go through. What is R1? What is R2? Well, with these ones, R1, all of these have uncertainty. So R1 is 680 plus or minus 27.2 ohms. How do I get that 27.2? If I go back, slide, all these have a percentage, as you can see up at the top. And so 680 times 4% is 27.2. That's how I got that. And then R2 also has some uncertainty, so it's 47 plus or minus 1.175. That is ohms. But a lot of people forgot about this. E in from the problem also said it had a little bit of uncertainty. So that is 5.05 plus or minus 0.18 volts. And what kind of problem is this? That's right, it's a multivariable problem. So what I have to do now, if you feel good about derivations and you can do partial derivatives, you're okay with the R1, R2 in the denominator, whatever, go for it. That's totally fine. For me, I thought, this is a little bit difficult. So what I chose to do was the sequential, where I'm going to make a table and I'm going to try to fill that out. And so that table looks something like this. So I'm going to have a section we have three different variables, each with their uncertainty. So we have R1 or R2. I'll start with R2, R1, and En. And what we're going to find is we're going to find R plus, R minus, change that R plus gives, the change that R negative gives, and then lastly, this is really just the average of those two. Sorry, it kind of zooms out on me. One important piece of information with this is I want to know what my nominal output is. And this is again, my function is E out. So what is my nominal E out? Well, if everything is as it says, 47, 680, 5.05, this is what I already calculated. This equals 0.326. If they're all at that nominal value, the problem is each has uncertainty, so we want to figure out what kind of wiggle room we have here. So if I change R plus is we're going to change, let's say for R2, instead of using 47 ohms, I'm going to use 48.175. And that goes both in the numerator and denominator. That changes my value to 0.334. If I take 47 and subtract that 1.175, that changes my output to 0.319. And so compared to the nominal resistance, or sorry, output of the function, this gives me a change of 0.008. And this is volts, by the way. All of these are in volts. And this would be a negative 0.007. And so the average of those is 0.0075. That's just the average. And this is the final column is what we're going to use when we do the root sum square at the end. Just like what is the average change that each of these factors gives to my multivariable system. So I do the same thing for R1. I'm not going to fill this all out. You can kind of do some of the math if you'd like. And then I do the same thing with En. So what happens if my input voltage is a lot higher or a lot lower? And that gives me something like this. And again, like I said, this is all in volts. All of these are in volts because that's what my output voltage is. And so after this, we can do the root sum square. So the uncertainty of the output voltage is equal to the root sum square of all three of these. And these are all in volts, so therefore my final answer will be volts. And we got plus or minus 0.018 volts. Or I could say that's 18 millivolts. So that is the uncertainty of our output voltage. There you go. I'll do another one.